Okay, first thing I thought I would do today is take a moment and do what I promised, which is go over what all you're going to have as far as what I'm going to drop and stuff like that. So, so what we're going to do is lab class quizzes, homework, attendance, and exams. Number taken to date, number to go, total, number dropped, and then points towards grade. Does that make sense? That way, everything, I want to make sure that we are all on the same page. And so originally I had 11 labs, but we've only done 1, 2, 3, 4, 5, 6, 7, 8. We've done 8 labs. We have 2 more to go for a total of 10 labs. Originally, I had planned to drop 1 lab, so I'm still going to drop a lab. Since your labs are worth 25 points, that means that you'll have 225 points towards your grade off of labs. Class quizzes. So far, I have 8. We have 2 more left. So again, that's a total of 10. Originally, I was going to drop 3, but I am now going to drop 2 of those. So that's going to be 80 points towards your grade. So it's not changing much. Homework. Next, yes. So right now there's 15 that you've got a grade for. And you will get 1, 2, 3. There will be 3 more for a total of 18. Which is a lot different than what we originally had. I will drop 3 of those homeworks, and I should have brought my calculator and did not. Actually, no, that's not fair because I had originally dropped how many? Originally, I was going to drop well, I was originally gonna drop 4 now, so that would have been 8. I'll drop 5. To be relatively fair. Of course, some of them I've given you credit for, so. Which is 32.5 towards your overall grade. Attendance, your attendance is still about the same. Minus we missed 2 days. So that would be 27 should have been the total. I will drop a total of 4. That's 2 weeks worth of attendance that I'm dropping. Technically 3 because we missed an entire week already. So at one point, so the total would have been 7 and 4, 31. And if I'm dropping 4, oh, no, sorry, that 4 is not to go. That's how many I was going to drop. How many do we have to go? We have 1, 2, 3, 4, 5 to go. And then exams, we've taken 3 exams. There's 1 more to go for a total of 4. I will drop an exam, so that's 450 points. As you can see, your lab is constituting a significant portion of your grade, which should help everybody's grade. So 580 plus 25 plus 450. If I added this up correctly, that means that your grade will be out of 812.5 instead of the 1,000 that it was originally going to be out of. From day 1, I've tried to get feedback. Does this seem reasonable to you? And like even though I've had to change it up, like I'm requesting still too much? Or does it seem pretty reasonable? If you look at that, that means that over 1/4 of your grade is from lab. So that's about right for a 4-hour class, where 1 of those hours comes from lab. So over 1/4 of it's coming from your lab grades. And about another, let's see, 80, 90, 100, 132.5 is coming from, so about 132. So over 10% of the grade is or 8% of the grade comes from homework and all that stuff. So, okay, as long as this seems fair, then I'm going to take a photograph. If I was putting it together on the spot. And that's what I'll judge out of. Any questions for me? Again, you're welcome to say if you don't think something up there is fair. But I tried to make it as reasonable as I can. I feel like I can. So only about half the grade comes from your exams, a little over half. Speaking of exams, you will get your exam back on Tuesday of next week. I've got it part of the way graded, but not completely. I had one of my dogs had an incident, not this one, but one of my dogs had a accident and had to have 8 stitches over the weekend. So I've been babysitting her, trying to keep her from tearing out her stitches, because she did the very first day she got them. She tore out a stitch. She's a little escape artist. So I've had to babysit her more this week than I had expected. So you will have a homework that's due on Monday. And on Monday, we will be doing, I believe it's the DNA extraction lab. So that'll be cool. We'll be basically just extracting DNA from strawberries. Anybody allergic to strawberry juice? We have gloves, but I have to make sure nobody's allergic from strawberry juice in the air. Okay. And if you have not turned it in, your fat and chips lab will be due Monday as well. So you'll have a homework due on Monday. We'll do the DNA extraction lab on Monday. You'll have a quiz due on Tuesday over the material we're covering today. And you will have the fat and chips lab due. Okay, so we are going to get back into carbohydrates. Technically, most of this chapter 20, we've actually done a lot of. We've got some bits and pieces that need to still be discussed related to the to this chapter, but we've done a lot of it. So just to bring us up to speed, we're going to be talking. Now, what I'm showing on the screen, the first couple of slides I actually did prior to the exam. So keep that in mind. First of all, carbohydrates are nothing but polyhydroxide aldehydes and ketones. You can have monosaccharides, which means you have a single sugar. You can have disaccharides, meaning you have 2 sugars combined, and then you can have polysaccharides. To make a disaccharide and a polysaccharide, we're going to do so using a glycosidic bond. Monosaccharides are simple sugars. They're comprised of 3 to 7 carbon chain. That is an aldehyde or a ketone. The aldehyde is referred to as an aldose. The OSE is indicative, the ending OSE is indicative of a sugar. So glucose, hexose, fructose, those are all sugars. And so they all end in ose. Again, an aldose is going to be one that has an aldehyde on the first carbon in the chain. And then you have ketose. Ketose is going to have the carbonyl group on the second carbon in the chain. When we look at whether we're looking at an aldose or a ketose, when you're looking at a simple sugar, the very last carbon in the chain is going to be a CH2OH group. If you are talking about a ketose, the first and last carbon in the chain is going to be a CH2OH group. Otherwise, any carbon between the carbonyl and the last CH2OH group is going to have an OH and a hydrogen on it. So that is going to be our monosaccharides. Any questions about the monosaccharides? By the way, before I continue, as I said the very first day of class, I'm going to say again, your last exam, instead of it being a true final, is going to simply be an exam over the information we are covering from here to the end of the semester. So it's going to be a semester exam rather than what most finals are, which is comprehensive. Okay. So simple sugars do have common names, and a lot of them have common names like glucose and fructose. But we can also name simple sugars using a systematic naming system. The first thing is whether or not it has an aldehyde or a ketone. If it's an aldehyde, it's an aldose. If it's a ketone, its prefix is a ketone. Then you indicate the number of carbon atoms in the chain, di, tri, tetra, etc. So di, tri, penta, tetra, penta, hexa, hepta, octa, nona, deca, even though we really don't go past hepta. So you indicate the number of carbons in the chain, and then you end it with ose. So if you're talking about an aldohexose, it's going to be a 6-carbon chain. It is going to have an aldehyde group on the first carbon. Carbon 2 through 5 is going to have an OH group, and it's going to have a hydrogen. And then it's going to, the last carbon in the chain will be a CH2OH. If you're talking about a ketopentose, pent means 5. That means there's 5 carbons. The second carbon has to be the carbonyl because it is a ketone, meaning the first and 5th carbon are CH2OHs. So carbon 3 and 4 are going to be the ones with the OH and the hydrogen. By the way, all the carbons between the carbonyl carbon and the CH2OH are going to be chiral. All the carbons between the carbonyl and the CH2OH will be chiral. I believe this is where we stopped on the day prior to the exam, with this general set of definitions related to how to systematically name sugars, simple sugars. So these are examples of some simple sugars that are extremely common simple sugars. The very first one is that of a glucose. As you can tell from glucose, first of all, it has an aldehyde group. So it's a aldo. Glucose has 6 carbons in the chain. That is why it is a hex. And then since it is a sugar, it's a hexose. So glucose is a aldohexose. Glucose is an extremely important simple sugar that you need to know because it is the monomer, the building block of starch and cellulose. And really the difference between starch and cellulose is going to be in the glycosidic bond. between the glucose monomers. Another important one that's in RNA is ribose. Ribose is a 5-carbon aldehyde. So it's aldopentose. It's a component of RNA and it's a component of ATP. So it's an extremely important component of a lot of things that go on within the body. And then you have fructose, which is probably it is the simplest, or one of the simplest, and the most common of the ketoses. So it is a ketopentose. Since it's a ketone, it's got the carbonyl carbon on the second carbon of the chain. It's got a CH2OH on both the first and last carbon of the chain. And then between it's a ketohexose. And then between the carbonyl and the last CH2OH is OH and hydrogen. I'm sorry. This diagram is on page 628 of your textbook if you want to look at it in further detail. As I mentioned, everything between the carbonyl carbon and the CH2OH on the last carbon in the chain are going to be chiral carbons. So glycerol, what that means is if we were to look at these individual groups, on this middle carbon here, that's going to be a chiral carbon, meaning it has 4 unique groups on that carbon. Those unique groups are a CHO, an H, an OH, and a CH2OH. Basically, all I did was I took and anything that's attached to that carbon. And you'll notice that they are all different. They have different numbers of hydrogens, different numbers of oxygens. So they're all different. Now, we can go in and we can number, or I'm sorry, we can add up the masses for these. So this is 16 from hydrogen, 16 from oxygen, 1 from hydrogen, for a total of 17 grams per mole due to the OH group. You have 12 from carbon, 1 from each of the hydrogens, so that makes it a total of 15, plus 16, so that makes it a total of 31. Yeah, I can't add. Hydrogen is just 1 gram per mole. And then you have your CHO, that's 12, and 16 is 28, plus 1 hydrogen is 29 grams per mole. That's another way that you can determine whether they are different. Not only can you list out the various components that are on that chiral carbon, but you can also list out the masses. And so you can do the same thing with the other. Now, to figure out which way it goes, basically we always are going to go to where you start with the carbonyl and you end with the hydrogen. And you want to go with the most masses. So in this particular case, it rotates right. So that's why it's called D-glyceraldehyde. If you do the other one, it rotates left. So that's why it's called L-glyceraldehyde. D is dextrose or dextro, and L is left. Now, what that means, with everything I just said, is let's just quickly look at this one. I don't have to write everything out to figure out the chiral carbons. Because one of the first things I said was everything between the carbonyl and the CH2OH would be chiral. So this one has 4 chiral carbons. Meaning that if I were to write out all the groups, on each carbon I would find 4 unique groups. Let me just show you with this first carbon. So if we're talking about carbon number 1 here, we have a CHO, an OH, and an H. And then on this bottom one, we have 1, 2, 3, 4 carbons. We have 1, 2, 3, 4 oxygens. And we have 1, 2, 3, 4, 5, 6 hydrogens. So again, you can list it out if you want. Now, the question is it D or is it an R? And D or R is going to be based off of the last one. D or R gets based off of the last one. So this one is going to be a D aldohexose. Okay, so the very last carbon is what the directionality is going to be based off of. You can either do it using what we did earlier and adding up the masses. But basically what you'll remember is it always starts with the aldehyde or the ketone and always ends with the hydrogen. So for this one, it would still be right. But another way to help you remember it, OH on right is a D, OH on left is an L. So that's a fast way. But it does come from how it would spin going from the aldehyde or ketone all the way to the hydrogen. Okay, so what does D and L mean? When we say something is D or something is L, what are we really talking about? So you have just a general light source that passes it through a polarizer, which causes all of the light to line up. It then passes through the sample. And what we're looking for is, does it turn it right or does it turn it left? That's ultimately what we're looking at. Is when the light source passes through the polarizer, which way does it polarize the light? Does it turn it right or does it turn it left? Any questions so far? But you can predict it by using the flat structure. You can predict which direction it's going to rotate it simply by starting with the carbonyl and seeing what, and ending with the hydrogen and see which way you have to go to get through all of them. Do you go to the right to get through all of them, or do you go to the left to get through all of them? Okay. So you should know this rule of thumb. The rule of thumb is that there's 2 to the nth possible stereoisomers and half that amount of enantiomers. where N represents the number of chiral carbons. So in the example here, there are 2 chiral carbons. So 2 squared is how many different stereoisomers there are. So there are 4 stereoisomers. Then there's half that many that are distereomers. What a distereomer is its mirror image. So on a rethros, which is this 4-carbon aldose, you have 2 forms of erythros that are distereomers of each other. One will be R, the other one will be L. So you have D erythros, which is the R, and you have L erythros, which is the left. Threose is another set of stereoisomers for the 4-carbon aldose. Again, you will have a D-threose and an L-threose. With this form of 6, an aldohexose, there are 4 chiral carbons. So there is 2 to the 4th stereoisomers. Or in other words, 2 times 2 is 4, times 2 is 8, times 2 is 16. So there are 16 stereoisomers. Therefore, there would be 8 diastereomers. Or 8 enantiomers. Out of these 16, 8 will be D, 8 will be L. We could try to draw all 16, but that's going to take quite a bit of effort. I won't make you draw that many stereoisomers. So what will I make you do? That's a good question, right? Let's talk about how to draw, and I won't go past 4 because that's a lot. So I won't go past erythros and threose. So let's talk about how to draw them. First of all, we need to understand what these lines mean. And the wedges. When we're looking at a diagram in this format, the lines mean that that is going away from you. So this C double bond OH is going away from you. As well as for carbon number 1 of the stereoisomer carbons, excuse me, of the chiral carbons. For carbon number 1 of the chiral carbons, all of this from below that is going away from you. So you have one going away and you have the other going away. The wedges means that it's coming to you. So the hydrogen is coming towards you, the OH is coming towards you. Now, I'm not going to expect you to draw it necessarily that way, but I did want to explain it because you're going to see it quite a bit. So let's talk about how to draw it. Let's talk about what they did. Okay, so in all cases, the very top piece remains the same. And the very bottom remains the same. We already know that there's 2 chiral carbons. So that was 2 squared. So that's 4. So you can draw out the base structure 4 times. The next thing you will notice that they did is they have pretended, remember there's 2 sets of enantiomers. Enantiomer set 1 and enantiomer set 2. And basically, what we mean when we say enantiomers is we're describing mirror images of each other. What they then did, even though this one doesn't look like a mirror, let me make it look like a mirror at least. They said, okay, both OHs are going to be on the right side on this first one. If this is a mirror, that means on the other one, the OHs are going to be looking at you, and the hydrogens are going to be opposite. For this next one, they said, okay, we've already got that, so let's put the OHs on the opposite sides. And then if I have a mirror, this first one, the OH would be coming towards me, and the hydrogen would be coming towards me. And so there's the other set of enantiomers. So that's how we get to these, is you start by drawing the backbone, which is mainly the carbon chain, the carbonyl, the CH2OH, and the carbon chain. You calculate out how many there should be, and that's how many chains you draw. You then draw a mirror between each set of enantiomers we're going to draw. So again, an enantiomer means mirror. And then you can work through the individual sets. We could do this for the aldohexose if we wanted to. But I'm not going to do that to you on a test because it would take us a long time just to draw all of them. A triose and a tetrose are going to be the maximum you'll have. So you could have a triose or you could have a tetrose. So on a test, you may have to draw out trioses, tetroses. On a test, I may ask you how many how many stereoisomers and how many enantiomers a hexose or a heptose can have, but I won't make you draw them. I may ask you, I may give you a set of molecules and say, okay, tell me which of these are enantiomers of this molecule. And you have to figure out which one looks like the mirror image of that molecule. So important terminology here. Stereoisomers. A stereoisomer, first of all, is an isomer, meaning it has the same formula. And it's going to, in this case, have the same connectivity. There are enantiomers. Which are mirror images of each other. And then there are diastereomers, which are stereoisomers that are not enantiomers. So if we were to look at this, from 1 to 4, these are all stereoisomers. Because everything's connected the same. These two are enantiomers, as are these two. However, these would be diastereomers. As would be those. Questions? So questions about how to get to how many stereoisomers there are. Questions about how to get to the number of enantiomers there are. If I were to give you a molecule and ask which of these is an enantiomer of it and gave you the other 3, could you tell me which one's the enantiomer? If I gave you a molecule and asked which one or ones are diastereomers, can you give me the diastereomers? And this just defines diastereomer, which I've already done. Okay. What I've been drawing up here, the simplest way to draw a sugar in its linear format is to use what is known as a Fisher projection. And I've actually already explained what a Fisher projection is. Basically, it takes a 3D image and it flattens it on the page. In this particular case, the things that are going down wind up as the vertical lines. And the things that are going left and right wind up as the horizontal line. In other words, it's kind of like taking an anvil and just pressing down on all bonds and flattening them out. That is how we get a Fisher projection. So what I was describing earlier, and another way to actually, this is a Fisher projection, which is the most common way I draw it. But what I was describing earlier is you can see the shape of the molecule in the Fisher projection because the vertical lines means that it's going away from you. And these wedges means that it's coming out at you. Again, a lot of times when I draw a sugar, it's going to be in this format. If I were to look at it, vertical lines means they're going away from you. Lines that are parallel to the floor means that it's coming towards you. you will notice that no matter what, I've always placed the aldose, the aldehyde piece, at the top and the CH2OH at the bottom. That is done on all of these Fisher projections. If I had a ketone, it would be on the second carbon always, and CH2OH on the bottom. In other words, all I'm doing is going back over some of the things I've already explained. We've already talked about this too. Monosaccharides are divided into D sugars and L sugars, depending upon which way they rotate the light. In the D sugar, the OH on the chiral carbon furthest, remember I always went to the one at the very end, furthest away from the carbonyl is going to be pointing on the right of the Fisher projection. For an L sugar, it's always going to be pointing on the left of the Fisher projection. So pointing right, D, pointing left, L, pointing left, L, pointing right, D. It is always about the last one, because all of them are chiral, but it's always about the last one with the naming of D and L. That's why I said there's in the hexoaldo or aldohexose, there is 16 of them. 8 will be D, 8 will be L. Okay. We have actually already gone over this piece of the puzzle in the sugar lab that we did, the monosaccharide lab that we did, and that is simple sugars do not typically exist in this linear format. They typically exist in the cyclic format that has a hemiacetal or a hemiketal. So this goes back to what we did in that laboratory where we made a hemiacetal or a hemiketal out of a simple sugar. Now you can't have a hemiacetal or a hemiketal with a 3-carbon chain, and it's very unlikely to have one with a 4-carbon chain. Hemiacetals and hemiketals start with 5 carbons, and so you typically have 5 or 6 carbon sugars. The reason for that is if you have anything less, you're going to have an extremely strained molecule, and it's not going to be able to exist in a strained format. So again, a triose and a tetrose, they're not typically going to be in a hemiacetal, hemiketal format because of the strain. But pentoses and hexoses and heptoses, they do tend to exist in the hemiacetal, hemiketal format. So just as a reminder of how we make a hemiacetal, hemiketal, the oxygen on the last chiral carbon, the one that we have used to determine whether it's D or L, that oxygen is going to attack at carbon number 1. Causing this CH2OH to flip up. The CH2OH, when we draw a simple sugar, is, I'm not going to say always, because that would probably be a lie, but 90% of the time it's going to be up. For this class, it's always up. So it flips it up, aligning that OH group. Again, we're talking about the last oxygen. It's that oxygen that attacks the carbonyl to make the ring structure. Now you will notice if the hydroxide group pointed left in the Fisher projection, it points up in the hemiacetal. If the hydroxide points left in the Fisher projection, it points up in the hemiacetal or hemiketal. If it points right in the Fisher projection, well, these two, if it points right in the Fisher projection, it's going to point down in the hemiacetal, hemiketal. Now, when this oxygen attacks the carbonyl, it'll make a hydroxide group. The carbonyl will, because it will break that carbonyl double bond. When the oxygen attacks the carbonyl carbon, it's going to break the double bond to make a new hydroxide group. Now, basically what happens is that hydrogen in the original hydroxide group, the hydrogen is transferred to the carbonyl oxygen. And that hydroxide group that is formed from the original carbonyl will either point up or it can point down. We can't control it. You're going to get what's called a racemic mixture. If it points up, then it is called a beta. If it points down, it's called an alpha. So you will notice that the rest of the name comes from what it looked like in the Fisher projection. So this was a D-glucose from the Fisher projection. So if it's a beta D-glucose, it means that the hydroxide point, that was the original carbonyl oxygen, that hydroxide is pointing up in the cyclic form. If it's an alpha D-glucose, it means that that hydroxide is pointing down in the cyclic form. So notes to take to keep everything straight. It's the oxygen on the last chiral carbon that does the attacking. To make the hemiacetal or hemiketal. The CH2OH of the hemiacetal of the aldehyde or the ketone points up. The CH2OH of the aldehyde or ketone points up. In the cyclic form. If an OH is on the left, in the Fisher projection, then it points up in the cyclic form. If the OH is on the right in the Fisher projection, then it points down in the cyclic form. Other key components is how we name the cyclic form. We keep the original name from the Fisher projection, but we attach either alpha or beta to it depending upon the directionality of the OH that's formed from the carbonyl oxygen. If the carbonyl oxygen points up, it's beta. If the carbonyl oxygen points down in the cyclic form, it's alpha. Any questions? When we get back on Tuesday, one of the things we're going to talk about is the a little bit more about glucose and other monosaccharides. And then we're going to get into some polysaccharides. But we've got a lot of monosaccharides still to go. So, questions? Okay, I will see you on Monday. I'll see you for DNA extraction on Monday.